We tend to think of the sun as this constant, unchanging ball of fire up in the sky. But that couldn't be further from the truth. It's actually a super dynamic, living star with this powerful rhythmic cycle that, believe it or not, shapes our entire solar system. So today, we're going to pull back the curtain on that secret cycle. I'm not kidding. Our sun literally has a heartbeat. It's this deep, powerful pulse, a rhythm that beats with just incredible regularity. And this isn't just some abstract science thing. It affects everything. We're talking space weather, the satellites we use, even the power grids right here on Earth. And here's what that heartbeat looks like when we chart it out. For, get this, over 150 years, we've been tracking it by counting these little dark blemishes you see on the sun's surface. We call them sunspots. And when you plot them over time, you get this absolutely beautiful, predictable pattern. A big peak in activity, then it gets quiet, then another peak, and the whole thing repeats, like clockwork, roughly every 11 years. Now, a pattern this regular, this consistent, it's no accident. It's a huge clue that there's some kind of powerful engine churning away deep inside the sun. So, the big question is, what's the secret? What's driving this cosmic rhythm? All right, let's dive in. To really get a handle on what's powering this thing, we got to start with the most obvious clue we have, the sunspots themselves. Because, it turns out, they tell us a ton about the sun's invisible magnetic field. So the official name for this whole thing is the solar cycle. But here's the key takeaway, the thing you absolutely have to remember. It's not really about the spots. The spots are just the symptom. The real story here is about a cycle of magnetic activity. The sunspots are just the breadcrumbs, the visible clues pointing to this massive, invisible process happening across the entire sun. Okay, so what's so special about these spots? Well, they aren't just random dark patches. They're actually areas of incredibly intense magnetic fields poking through the surface. You can think of them as windows, letting us peer into the sun's powerful and, as we're about to see, surprisingly organized magnetic engine. So back in the early 1900s, an astronomer named George Hale made a breakthrough discovery. He realized that sunspots almost always show up in pairs. And these pairs act just like tiny bar magnets, with a positive and a negative pole. This one observation unlocked a stunningly consistent set of rules about how the sun works. We call it Hale's law, and it's pretty wild. It basically works like this. Each sunspot pair has a leader and a follower. In the sun's entire northern half, all the leading spots will have the same magnetic polarity, let's say positive. At the same time, down in the southern half, all the leaders will have the opposite polarity, negative. And then, and this is the crazy part, when a new 11-year cycle kicks off, the whole thing flips. Now the north is negative and the south is positive. This isn't just a fluke. It holds true like 92 to 95% of the time. That tells us there's some serious organization happening inside the sun. But wait, there's more. The organization doesn't stop there. These magnetic pairs aren't just lined up perfectly east to west. If you look closely, you'll see they're actually tilted. The leading spot, the one out in front as the sun spins, is almost always a little closer to the sun's equator. This is called Joy's law, and while it's more of a trend than a hard and fast rule, it's super consistent. And get this, the farther a sunspot pair is from the equator, the bigger that tilt gets. So now we've got two major rules of the road for sunspots. Hale's law telling us their magnetic polarity, and Joy's law telling us how they're tilted. The plot thickens, right? Okay, so why am I telling you about all these little rules? Because when you take a step back, you realize these individual rules all add up to something, well, breathtaking. A massive, beautiful pattern that only reveals itself when you watch the sun for decades. Just imagine for a second. Imagine you could track the location of every single sunspot that appeared, every day, for over a century, and then plot all those little dots on a single chart. What would you expect to see? Just a random, chaotic mess, right? Nope. What you get is one of the most iconic and beautiful diagrams in all of science. This. They call it the butterfly diagram. And you can see why, right? At the beginning of each 11-year cycle, the sunspots pop up in the middle latitudes, both north and south. But as the cycle goes on, they start appearing closer and closer to the equator. Over time, that migration traces out these incredible patterns that look just like a butterfly's wings. Okay, this is where it gets really cool. If you plot the magnetic field data instead of just the visible spots, you still see the butterfly wings, but you also see something new. These faint streams of magnetic energy, kind of leaking from the sunspot zones and drifting slowly towards the sun's north and south poles. So what's the deal with these streams? Are they important? Oh yeah. They're not just some random leftover effect. They are basically the memory of the current cycle, and they become the seed for the next one. In fact, tracking them is the key to predicting what the sun's going to do next. Okay, take a look at this. This chart is tracking the magnetic field right at the sun's poles. All that magnetic stuff we saw flowing towards the poles, it piles up there, and eventually it gets so strong that it cancels out the old polar magnetic field and replaces it with a new one that's completely reversed. The sun's entire north and south magnetic poles literally flip their polarity right around the peak of the sunspot cycle. Mind-blowing, right? And here's the kicker. The reason this is so important. How strong those new polar fields are at the very end of a cycle, what we call the solar minimum, that is the single best clue we have for predicting how strong the next cycle is going to be. It's the cornerstone of solar forecasting. But, as always with the sun, there's a twist. Yeah, there's a wild card in the deck. Every now and then, the sun throws a curveball. It produces what scientists call rogue active regions, sunspot groups that don't play by the rules and can have a huge, outsized effect on how the whole cycle plays out. So what makes a sunspot rogue? Well, it could be absolutely gigantic. Or maybe it has a really weird tilt that totally defies Joy's law. Or it pops up way too close to the equator. These are the troublemakers. Just one of these rogue regions can dump so much magnetic material into that poleward flow that it completely changes the game and throws all our predictions for the next cycle right out of the window. Okay, so we've seen these incredible patterns on the surface, we've learned the rules they follow, and we've even met the wild cards that can break those rules. But you have to remember, all of this is just what's happening on the surface. It's all just a symptom. So what's the real engine driving this whole machine from deep inside the sun? Well, here it is. The answer seems to be these enormous, slow-moving rivers of plasma called the meridional circulation. The best way to picture it is as a giant conveyor belt on a planetary scale. At the surface, plasma flows toward the poles. That's the stream we saw carrying all that magnetic junk. Then, it sinks down deep inside the sun and flows all the way back to the equator, ready to start the journey again. This conveyor belt, that's the engine. It's what carries the magnetic fields around, what stretches and strengthens them, and what ultimately sets the 11-year tempo of the entire solar cycle. That heartbeat we talked about at the very beginning? It's the slow, steady, powerful rhythm of this massive, hidden conveyor belt. So we started with just simple dark spots on the sun's surface, and we followed this trail of magnetic breadcrumbs all the way down into the solar interior, uncovering this incredibly complex, deeply connected system. We've seen the patterns, we've found the engine, but it really makes you wonder, doesn't it? What other secrets, what even deeper rhythms is our sun still hiding?